Our next set of notes deals with the concentration of ions in solution. But before we want to talk about concentration of ions, let's review a little bit about concentration in general. When we're in chemistry, we virtually always deal with concentration in terms of molarity. And remember, molarity is the number of moles of our solute, whatever that solute may be, whether it is salt or sugar or whatever, divided by the number of liters total of solution. What is the total volume of the solution? Now, generally, we write that as simply molarity equals moles over liters. But if we're dealing with mass, we have some situation where it gives us the grams of the substance involved, or it asks us about the mass of the substance. Then we need to remember that we can always find moles by simply taking the mass of the substance divided by its molar mass, or mass over molar mass. A nice curly Q M for molar mass. So we've got lots of M's in this, and it's really important that we write our variables correctly so it's not any more confusing than it already is. So molarity can also be written as mass over molar mass over liters. So depending on what it gives us and what it asks us for, we'll determine which of those two equations we want to use. In this particular case, the review example, determine the molarity. It's asking us to find the molarity of a solution, and it tells us that we have 1.22 grams of Ki, potassium iodide, dissolved in water to make 250 milliliters of solution. So as soon as it told us that we had grams of potassium iodide, we hopefully realized that we need to use this equation, the mass over molar mass form of the equation. So let's get that down. Please, please, please. It's no different now than it was in pre-AP, if not more important to put your equations, because AP expects your equations to be there and your substitutions to be shown, or you don't get credit. So the molarity is equal to the mass over the molar mass over the liters. Since we're looking for molarity, we don't need to rearrange the equation or anything. So the molarity is simply going to be the 1.22 grams of Ki divided by its molar mass. And if you look up the molar mass of both potassium and iodine and add them together, you get 166.00 grams per mole. We're going to divide that by the liters. Now be careful, because it almost always gives it to you in milliliters. So you might as well get used to the fact that when you're changing from milliliters to liters, you're moving 3 places back to the left. So we end up with 0.250 liters of solution. Plugging that in our calculators, then we come up with a molarity of potassium iodide of 0.0294 to 3 sig figs moles per liter. Look at what cancels. We're canceling grams, and all we're left with then is moles per liter. And since we're reporting this officially, we're going to take moles per liter and change it back into the term molarity. Moles per liter is molarity. So 0.0294 molar Ki. That's the molarity of our solution. Now, when we drop that Ki in solution, though, what happens is it's going to be dissolved by the water. And when it dissolves, that Ki is going to split into potassium ions. Review your charges if you need to review your charges on your periodic table for these different ions. A positive for the potassium and a negative for the iodine. So you've got 1 potassium ion and 1 iodide ion. And if we had 10 potassium ions to begin with, 10 potassium iodide particles to begin with, and we put them in water, we'd get 10 potassiums and 10 iodides split apart into ions. So if we've got 0.0294 molar potassium ion, then what we've got, if once those split apart in the water, once those dissolve, we've got 0.0294 molar potassium, and we've got 0.0294 molar iodine. It's important for us to know that when we dissolve something in water, what the concentration of those ions are going to be. Now that's a 1-to-1 relationship. There's 1 potassium for every 1 iodine. What if we've got a situation like the next example? In this case, we've got barium chloride. The first thing you've got to do is to decide how many of each ion you have. And in this case, we have 1 barium ion, and look up your charge on barium. Remember, it's a 2+. So we've got 1 barium ion. We've got 2 chloride ions. So if we've got 0.25 molar barium chloride, then let's use simpler numbers. Let's say we had 10 barium chlorides. Hopefully it makes sense that if we have 10 barium chlorides, we would end up with 10 bariums, but 20 chloride ions, because there are 2 chloride ions in that formula. So what does that mean? That means that we're going to have a 0.25 molar concentration for the barium ion, but we're going to need to double that concentration to get the concentration of the chloride. So 0.25 molar, excuse me, I'm sorry, I said double it, but then I didn't. 0.50, multiply it by 2, 0.50 molar chloride ions. So with that in mind, see if you can figure out what's going to happen in the next case when we're dealing with chromium and hydroxide. Remember, the first thing you want to do is to determine how many of each of the ions are present. Remember that the polyatomic ions don't split apart. So you should come up with the fact that you have 1 chromium ion, and since hydroxide's a negative charge, that means the chromium ion must be a 3+ to balance out those 3 hydroxides. And we've got 3 hydroxide ions. So that's what we're looking at in this solution. What does that mean? It means that we have 1.5 molar chromium, because there's only 1 of them, but since there are 3 hydroxides, we're going to need to triple that concentration to find how many hydroxides we're going to have in solution. So that's going to end up being 4.5 molar hydroxide. Once again, see if you can do the next one yourself real quick. Hopefully you tried that, and hopefully the first thing you did was to determine how many of each of the ions you have. Looks like we have 3 potassium ions, and hopefully you remembered that phosphate is a polyatomic ion. You've got resources to look that up. The phosphate is 3-, and there's only 1 of them. So if I've got 3 potassium ions, that means my concentration of potassium ions is going to be 0.33 molar for my potassium ions. And since I only have 1 phosphate, it's going to stay 0.11 molar for my phosphate. So how does that translate then in a more difficult type of problem whenever we're talking about mixing 2 solutions together, each of which has a different composition? In this case, if we look at this next problem, we have 100 milliliters of a 0.5 molar solution of potassium sulfate, and we have 75 milliliters of a 0.25 molar solution of aluminum nitrate. And we want to find the concentration of each ion in the solution. For one thing, we know that anytime we mix 2 solutions together, the concentration is always going to be moles over total liters. So the new concentration, whoops, that didn't turn out very well. The new concentration Looks like the smartboard is trying to be a little glitchy right now. Let's hope that's temporary. We'll try it one more time. The new concentration is going to be moles over total liters. Moles over total liters. So let's take each one of them at a time. The first thing we're going to do is to find out how many moles of each of the substances we have in the solution. So for K2SO4, if we have 100 milliliters, that's the same as saying we have 0.11 liters. And we're going to multiply that by its molarity. Remember, molarity is moles per liter. So look at what happens when we do this. When we divide by or multiply by moles per liter, our liters cancel, and we're left with moles. So that needs to be so ingrained in your head, I can't even begin to tell you that multiplying liters times molarity gives you moles. Liters times molarity gives you moles. I'm going to say it one more time. Liters times molarity gives you moles, because you're going to use that over and over. So when we do this, that gives us 0.050 moles of our K2SO4. Now, think about it. When you mix those two solutions together, you had 100 milliliters. You mixed it with 75 milliliters. So now we have a total liter value, a total volume of 175 milliliters. So I've got my moles of potassium sulfate, but now I'm going to divide that by the total number of milliliters, 175. Change that to liters, 0.175 liters, and I get a concentration of 0.29 molar K2SO4. Now, think about what we did above. If we have K2SO4, it wants concentration of all the ions in solution. K2SO4 has 2 potassiums and 1 sulfate. So, since there are 2 K pluses, that's going to be 0.58 molar potassium ion. But since there's only 1 sulfate, that's going to give us a concentration still of just 0.29 molar. So that takes care of the concentration of the ions after the solutions were mixed together for the potassium sulfate. See if you can do the exact same thing now with the aluminum nitrate. And hopefully when I ask you to do this, you actually do try to do it on your own, because that's how you know where your glitches are. And then when I go over it, you can see if you made any mistakes. When we have the aluminum nitrate, we want to do the same thing. For aluminum nitrate, we had 0.075 liters. Liters times molarity gives you moles. And we're going to multiply it by its molarity of 0.25 moles per liter. Liters cancel. We'll be left with 0.01875 moles of aluminum nitrate in the same quantity of water. It's mixed 100 plus 75 milliliters, so 175 milliliters or 0.175 liters of solution. We end up with a 0.11 molar solution of aluminum nitrate. Do the exact same thing you did in the previous problem. We know that we have 1 aluminum ion. Aluminum must be 3 plus since nitrates are -1. And looks like I didn't put my final 3 down there. So if I've got 1 aluminum 3 plus, that means my molarity of aluminum is still 0.11 molar. but it looks like I have 3 nitrates. And if I have 3 nitrates, then my concentration of nitrate is going to be triple that. So 0.33 molar nitrate. Now would be a good time for me to mention that you need to really pull out your polyatomic ion list. It's in Unit 4 notes from pre-AP, or you can look it up on the notes online so that you have access to these charges for nitrate and sulfate and phosphate, etc. So just as a reminder of where you can find that information. You can always Google it, but okay, our final example deals with mixing 2 solutions now that are composed of the same thing. We've got 2 different concentrations of solution of iron trichloride, and we're going to mix those 2 solutions together, different amounts of each solution, and we want to know the resulting molarity of the solution. So remember, molarity is still moles over total liters. And we're looking at the molarity of the solution itself, not of the ion. So that's going to make it a little bit easier. So the molarity of FeCl3 total is what we're looking for. So moles over total liters again. Let's get moles of FeCl3 in each of our solutions, and then we'll divide by our total liters. So liters times molarity gives you moles, so 0.050 liters of our 0.125 molar solution, moles per liter, is going to give us a mole value of 0.00625 moles for our first solution. That didn't come out very good, did it? Let me rewrite that. 0.00625. And now let's get moles from our second solution. In the second solution, we have 0.025 liters. And we're going to multiply that by our molarity again for our second solution, 0.220 moles per liter for FeCl3. And when we multiply that together, we are going to get 0.0055. Looks like the smartboard's trying to glitch on us again. It'll just hold together for this last problem. We'll be home free. 0.0. I'm writing slow, hoping that it will hang with me just a little bit longer. 5. Not sure why it's glitching, but I'd rather not start these notes over again. Moles. So now all we need to do is to add those 2 mole values together, since it's the same substance in the solution, and divide by total liters. Looks like we've got 50 milliliters added to 25 milliliters. So we're going to end up with a 75 milliliter solution. So when I add these 2 together, I end up with 0.01175 moles. It's going really slow. Well, if y'all get bored, you can always double time me. So 0.01175 moles divided by 0.075 liters, or 75 milliliters. And if I can just get this answer written, it will be done. 0.1626 molar Fe Cl3 total concentration. So we made it. A little slow at the end, but we're done.